Volume check. Is this good in the back? Great. Then let's get started. Okay, so today we have two distinct topics, which admittedly are both getting very short treatments. Not really two topics that we're going to spend a whole lot of time discussing, but good for you to know about at some high level regardless. Okay, so last time we started looking at the problem of how do we actually learn the best models that really accomplish the goal that we're trying to accomplish, which is to have models that generalize well, right? At a very superficial level, we can construct the objective of do well on your training data, but at the end of the day, that's not actually what we care about, right? What we want is a model that not only does well on the training data, but also generalizes well to data that it hasn't seen yet. And that was the, sort of the question that we explored last time. And we explored it through the lens of these concepts of overfitting and underfitting, right? If we want to train a model or learn a model that has minimal generalization error, we need to make sure that the model that we learn is neither overfitting nor underfitting, right? So underfitting is basically, it's not actually doing well enough on the training data. It's somewhat more straightforward to deal with that problem. It just means that we need a better model, right? Overfitting was a little bit more tricky, where maybe we're doing really well on the training data, but we're not generalizing well. And for that, we needed concepts from validation in order to combat those issues, right? We needed to split off a set of training data that we could use to estimate the true risk so that we could compare that to the empirical risk and then try to diagnose that way if we were overfitting, right? And then if we did all of that and then tuned our hyperparameters correctly and all of that kind of stuff, then we could get to models that were neither overfitting nor underfitting, and those are the models that we really want, right? The models that have minimal generalization error. So today we're going to take a brief look at this concept of generalization error, and then also extend that into two distinct topics, which admittedly kind of don't really have anything to do with each other, but they kind of both fit into this lecture. So part of what we're going to do today is trying to understand generalization error. So, when my model might make mistakes, right, on data that it hasn't seen before, how do I characterize those mistakes that my model is making, and how do I understand why my model is making those errors, right? And so one way that we can do this is via what we call the bias-variance decomposition, which is a very famous idea. You actually might remember from lecture 1 that we gave this pictorial representation of what bias and variance look like, right, with the bullseyes. So that's a good thing to go back to because it's a good intuition. And specifically, we'll do this for regression models because it's a whole lot easier to do this for regression models, although it is possible to do it for other types of models like classification as well. And then with whatever time we have remaining, because the first part might take quite a bit of time because there's a lot of math, for whatever time we have remaining, we'll then digress into classification and then try to understand how different problem settings in classification, where we're maybe allowed to make different types of decisions or different decisions have different ramifications, actually affects the decision rule that we want to use, and then how does that in turn affect the generalization error that we might get. And so very broadly speaking, these types of questions are covered by the area known as decision theory, which is a very rich area with a lot of interesting work. We're essentially covering these two things in a comically short amount of time each. I mean, they each get half a lecture. That's not a whole lot of time, but it's sort of meant to give you a taste, a flavor of what these kinds of things look like. And then if anybody's interested, there's always a lot of great resources for learning more about these things. But that's what we're doing today. And we're starting today with the bias-variance decomposition, and this is the part that is going to have a lot of math. So, like I said, we're going to focus on this for regression, okay, because things are just a lot easier for this particular setup when we use regression. And some of these things, probably look quite familiar to you. So the outputs, right, are scalar real values, and then we're given a data set of n data points, xi, yi, right, where, remember now, these yi's are these scalar real values. And then we have to define, some underlying data generating process that we think describes the x's and the y's that we're seeing. How were the x's and y's sampled, right, in my data set? And so very, very generally, right, so we're not going to place a whole lot of assumptions on this, but we're going to assume that my x's were sampled from some, this is very large. Let's switch to, okay. My x's were sampled from some distribution, which I'm going to call p of x, okay, p sub x. And sort of like what we had been doing, remember when, like, think back to like MLE and all these discriminative models that we've learned, right? Like what we're assuming here is that we don't really have any control over this distribution over x, right? It's just some distribution where my x's are coming from. It exists. That's how the x's are sampled, but I have no idea beyond that how I might actually characterize it. But as it turns out, if I, sort of just abstract it away, then it doesn't really matter, right? All I care about are these discriminative models anyway. And then what I'm going to assume is that there's some conditional relationship between y given x that has a very particular form. The form is that there's a function f, and this is kind of the thing that I'm trying to estimate, right? I'm trying to estimate what this underlying function is. Maybe it's like linear, right? And then I'm trying to use like linear regression or ridge regression or something like that in order to figure it out. But there's some underlying function f that describes how y is generated, but it's not deterministic, right? Because there's some additional noise epsilon that factors into the overall procedure. And then, by appealing to the central limit theorem, it's pretty reasonable to assume that maybe this epsilon itself follows some normal distribution, okay, with mean 0 and then some variance sigma squared, which maybe we don't know. Okay, so this is how we're going to assume that our data was sampled. X comes from some distribution p of x. We don't know how to control that, but let's just forget about it. And then y given x comes from, this function f, which is what I'm trying to learn, right, plus some additive Gaussian noise, maybe with some variance that I don't know, okay? So then the question that we can then ask is, given this setup, how might we be able to define a probabilistic model, right, that outputs a distribution over y given x? Well, one potential option, which is pretty simple, is that we could say that the way that I'm going to model y given x, okay, is going to be with a Gaussian distribution where the mean is going to come from this, this model that I'm learning. Okay, so the model is going to output the mean. Okay, so I'll call that f theta. So f theta is this model that has parameters theta. It takes in an x and it outputs the mean, which is just a scalar, right, of the y that I'm trying to predict given that x. Okay, and then I don't know what this sigma squared is, right? I don't know what's the noise attached to this epsilon, but as it turns out, it doesn't really matter. I can make some pretty simplifying assumptions. For example, I could just say that I'm going to assume that the variance here is 1, okay? And as it turns out, none of this really matters at the end because, once we put things into the negative log likelihood loss and all of these terms kind of like, they're just multiplicative constants anyway. They don't really factor into our optimization. But here's my model, okay? I'm going to model the conditional distribution of y given x as a Gaussian, where the mean comes from my model, and then the variance is 1. So then I can ask, well, what's the negative log likelihood loss in this case, right? So what is negative log p theta, right, of, some yi given xi, right? I'm just going to, I would sum these over all my data points, but, let's just look at what it looks like for one particular data point. Well, if I take the log of a Gaussian, right, then all those terms in the front, they kind of go away, especially because I assume the variance is 1, right? And then this exp, log of exp cancels out, so then all I have is the thing that's inside the exp, right? Which ends up looking something like 1/2, because my variance is 1, f theta xi minus yi squared, plus a constant with respect to theta, okay? So actually, this is actually just, it's a form of like squared error, right? And if I average this over all my data points, then I get mean squared error, right? So all of these things are kind of related to all the MLE stuff that we've seen before, just based on different modeling assumptions that we might make, right? So that's kind of nice. I ended up with something pretty simple, right? It's just squared error that I'm going to be looking at, right? So basically, what it is that we're going to try to do is we're going to try to understand how this squared error can be understood, how it can be decomposed into different parts that we can better understand for a new point that my model is being asked to generalize to. Okay, for a new point that my model wasn't trained on, that it's being asked to predict for, how well is my model going to do there, and how do I understand the errors that it's making? Okay, and that's going to be bias and variance. And so we're going to try to give a little bit of intuition first, right, as to what bias and variance actually mean. A good picture to keep in mind, if you can remember it, is sort of like those bullseyes that we drew in the first lecture, right, where bias means you're just systematically somewhere far away from the center of the target, whereas variance means that, your spread is larger, right? So those are like two different types of ways that we might not be able to hit that bullseye, and that's kind of the intuition that we want to keep here. But more specifically, actually, what we're going to be looking at is, well, first off, we assume that our training data was actually randomly sampled. We have this data generating process for our training data, right? Each x comes from p of x, and then each y given x is f of x, the true f, right, plus additive Gaussian noise, right? So our training data was randomly sampled. All of my xi, yi's are IID sampled according to that process, right? So then we can ask the question, well, what if I had some different training set instead, right? What if I reran this process and sampled a new set of training data? Then how would my model change, right? What other model might I learn depending on how I define the model and how I actually learn it, right? And here's some intuition for what that might actually look like and how it relates to actually the concepts of overfitting and underfitting that we talked about last time. So here we have overfitting and underfitting, okay? And let's actually break down this drawing a little bit. So here, this black line, okay, this black curve in each of these plots, it's the same across all of them, right? That represents the true function, okay? That represents f, okay? F is a true function that I'm trying to learn, and then all of these different orange curves represent, maybe the functions that I actually learn, okay? All of these blue dots are data points, x, I, y, I, that I sample from my function f. Okay, that's why they lie on the curve or close to the curve. And you can see that across these different plots, I'm sort of sampling different data points. Okay, I'm sampling different blue dots along that curve, based on just randomly redrawing data as my training data. So then what these plots are trying to show, let's focus on this one on the left here, okay? If I sample these 5 points from f, then what function do I learn? What orange curve do I learn? Versus if I sample these 5 points versus if I sample these 5 points, okay? Well, if my function is really expressive, or the model is really expressive, right? So maybe I'm using like a linear model, but I'm using like a really high order polynomial kernel or something like that, right? So then my model has a lot of expressivity in terms of what types of functions it can represent. If the model is able to do that, then it might overfit, right? It might overfit to the data if it's too expressive and if there's not enough data. And then what it would do is essentially potentially just learn a different function, right? A different f of theta for every single training set. Okay, why? Because it's given enough expressivity to really fit the data really well, right? So if I draw new data points, then my model is going to, learn how to fit those data points really well, and in turn sort of learn different functions every single time, okay, based on whatever data was provided for it, okay? Compare and contrast that to on this side where, for example, maybe my model is really underpowered, okay, maybe I'm not using featureization, I'm just using a linear model, and here we can obviously see that a linear model would be a bad idea because the function that we're trying to learn is actually some kind of curve, right? Well, if I'm learning a linear model, the intuition that we want to get here is that sort of regardless, right, of which data set I sample as my training data, the linear model that I fit, it doesn't really change all that much, right? It's not doing a particularly good job at all of fitting the training data, but it's also not really varying all that much, right? It's sort of learning a similar function, a similar model, regardless of what training data it's given. Even if I pool all of the data together, it's still going to learn a fairly similar function just because it doesn't have enough expressivity to actually model correctly the underlying function, okay? So if my model is underfitting, okay, maybe because it doesn't have enough expressivity, then it learns similar functions, even if we combine all of the training sets together. And the key thing to note here is that all of these learned functions are bad, right? None of them are really particularly good at representing this curve that I want to represent. And this is kind of, the pictorial depiction of these two different problems that I can run into, right? Maybe what I have is these functions are not all that different from each other, even if I have different training sets, but they're all bad in the sense that they're not even doing a good job at representing the training data, right? Or my model is really good at representing the training data because it's, very expressive. But if I don't have enough training data and I sample training data, if I sample different data sets, then my model is going to just learn how to really do a really good job of fitting that training data, and then learn a different function every time that's always overfitting, okay, not really representing the actual function that I want to learn. Okay, so that's the intuition behind these two different types of error, generalization error, that my model can make. And now what we want to do is kind of put that into math, into equations, okay? Yes? Yeah, great point, right? So the natural question is like, it seems like the more we featureize our data, right? So we have, these expressive features that we can work with, the better we might be able to represent the underlying data generating process, right? And in general, that is true as long as you have enough data, right? So you potentially need very large amounts of data in order to properly learn a model that's very expressive, that has, for example, a very high order polynomial kernel or something like that, right? If you only sample a certain number of data points and your model is overpowered, then we run into this problem where it could learn different functions every single time for a new data set, and that's certainly not, that's not particularly good. Okay. So here's what we're going to do, okay? What we're going to do is we're going to try to understand how well would my model predict on a new test point x prime, okay? So a point that my model was not actually trained to predict on, right? And then when I say expected, what I mean is the expectation over different training data sets that the model could be trained on, remember? Because that's a random procedure, right? Sampling a training data set and then training the model, we're treating that as random, right? So the way that we're going to write this is an expectation, okay? Oh, actually, you know what? Let me define a little bit of shorthand first. Okay, so here's our model parameters theta, right? But actually now, because we're assuming that the training data set is a random variable, right? Well, the theta that I learn is a function of that data set, right? Like think about like, linear regression or ridge regression or something like that. The theta that I come out with, theta star, is a function of x and y, right? So if x and y are random, then I can treat theta, right, as a function of this random variable, this data set, okay? So I'm going to let theta d be the maximum likelihood estimate, okay, just because we're using negative log likelihood loss, right, for a particular data set d, and this is my random variable, okay? And then for shorthand, let's let f of d be the same thing as writing f sub theta of d, okay? The only reason I'm doing this is so that I can save a few pen strokes, okay? So f of theta of d is the f theta, the model that I would learn for a particular data set d that was randomly sampled, okay? So then what I'm trying to look at here is the expected error or the expected loss, right? And here we're using squared error based on, kind of the probabilistic model that we defined, right? Of f of d on this new point x, right? Minus, well, what that actual label is for that point x, right? But the label, or, I should say the target, right, is itself a random variable. There's sort of additive Gaussian noise on top of that thing, right? So it's f of x, the true f of x, plus some epsilon, right? So we treat this thing as a random variable. That's why I give it a capital letter, right? And I'm looking at the expectation of, what my model is going to predict versus what the actual target is. Okay, so this expectation is over this data set D over here, right? That's the thing that I'm trying to take an expectation with respect to, right? The data sets that I could sample. But also this thing is a random variable too, so I need to take an expectation over that as well, right? Because y prime could be different depending on how that epsilon is actually sampled, okay? So this is the quantity that I really want to analyze, all right? Because this is the quantity that's going to tell me something about, on average, how well could I expect my model to generalize to a new test point x prime, at least in this regression setting, right? I want to understand this quantity because it's going to tell me, something that I really care about, right? Like, what's the model going to do on a new test point? How well does it perform? How do we sort of understand this quantity right here, this expected error, okay? In order to do this analysis, there's going to be one more thing that we're going to bring in, basically, essentially almost for notational convenience, and it's this f bar that we see here, okay? F bar of x, you can sort of think of it intuitively as sort of like the average model, okay? The model that I would learn on average if I sort of averaged over all the data sets that I could train on, okay? So in particular, the way that I write this f bar is that the prediction that it makes for a particular point x is actually just the average prediction where the average is taken over all the data sets that I could be training on that data point. Okay, so that's all of this f bar is trying to say. It's basically saying, like, let's take the data set out of the equation, okay? Let's try to get rid of the randomness that's associated with this random data set, D, and then just ask on average, if I trained across all of these different data sets, right, and then I averaged all those predictions together, what will my model say? Okay, that's what this f bar is trying to do. Okay, so now we've defined the quantity that we're actually interested in analyzing. That's this thing right here, this expected error, right? And then we've also defined sort of this notational convenience of f bar being the expected, the average model that I could learn over all my different training data sets. Now what we're going to do is a whole bunch of math, okay? And this math is typically referred to as the bias variance decomposition. You might also hear it as the bias variance trade-off, which is a point that we'll return to after we do all this math. So remember, this is the quantity that we want to analyze. It's FD, right? So remember, FD is shorthand, right, for the F theta that I would learn for a particular data set D, okay? Of x prime minus, what's the actual kind of like real label, real target, right, for x prime. The way that I'm going to start to analyze this is the way that all great mathematical analyses are carried out. Is I'm going to start adding and subtracting things, okay, because that's what everybody does. So what I'm going to do is I'm going to add and subtract f of x prime. Okay, remember, what is f? F is my true model, right? F is the thing that I would really want f theta to be if only the model is expressive enough and I have enough data, yada, yada, yada. But f is the true function that I'm trying to learn, okay? Minus y prime squared. Okay. Now, what I'm going to do, actually, is I'm going to sort of break out this, this expression, right, using FOIL, actually, where I'm going to basically, going to treat this term as the first term, and then this term as my second term. Okay, so then if I use FOIL, I get all these cross terms and all these things that look like squares. But actually, the thing that I get, which I don't have enough room on the slide for to show you, but let me write it out first, and then I'll explain what's going on. So we have this thing minus f of x prime squared. Okay, so that's kind of like the first term that I get here. And then I get plus y prime minus f of x prime squared. So I got like essentially like this term squared and this term squared. I claim that that's all I get because all the other cross terms are 0. Okay, why are all the cross terms 0? It's actually a bit of a mathematical exercise involving things like independence, linearity of expectations, all that other kind of stuff. But you know, if you are curious, I think it's an interesting exercise to work out. Okay, but here's what I get. That's just my claim, because there's not enough time to go into it in detail. But actually, let's take a look at the second term right here, expectation of y prime minus f of x prime. You'll notice that there's no d in here, right? I'm not doing anything involving like expectation over different data sets. This is actually just y prime, the true target, minus f of x prime, which is like the true model's prediction, or sorry, the true function's prediction, right? All of this, the only thing that this depends on is the randomness in y itself, right? Because there's no model that's being learned in the second expression over here, right? This is just asking how noisy is the process that generates y from x, right? Like how big is that sigma squared essentially, right? And in fact, we can see this even more clearly if we recognize that this f of x prime here, this is actually the expectation of y prime, okay? Because we assume 0 mean additive noise, right? So f gives the mean, right, of the y, but there's some noise that's involved here, so the expected squared difference between these two things might still be non-zero. In fact, we know exactly what this quantity amounts to. I don't know if this is a particularly straightforward question, but can anyone tell me what this expression simplifies to? Yes? Exactly. What was the variance of y? It was sigma squared, right? So actually, this whole term right here, this is actually just sigma squared. Sigma squared was the noise in the data generating process that I assumed, right? Yes? Oh, why does it not just equal 0? So one thing is, if I got rid of this square, it would equal 0, right? Because the expected difference between y prime and f of x prime is 0, but I'm squaring the error, right? So it's always going to be like something bigger than 0. So then that's what becomes the variance, right? Yeah. So this is actually a textbook definition of variance, which is why I get the sigma squared that comes out of it, okay? But actually, I'm not done here, right? Because I still have to analyze what this thing is on the inside. And, you know, in continuing our line of, you know, amazing mathematical insight, we're just going to add and subtract another thing from this expression. And what we're going to add and subtract is this f bar that I defined previously. Okay. Don't forget the sigma squared at the end that we've already worked out. Okay? Now I'm going to do something very similar to what I did going from line 2 to line 3, which is sort of break these terms out into their respective components, and then I claim again that a lot of cross terms cancel out. They turn into 0 because of independence and linearity of expectation and all those really useful properties, which is again not something that we're going to go into in a lot of detail, but it is a useful exercise if you so choose. So this thing ends up working out in the following way. What I end up getting is something that looks like expectation of fd, the model that I learn on this random data set D, right, minus f bar, which is like the average model that I could learn, right? And remember, this thing, f bar, is an expectation over fd, right? So I have fd minus expectation of fd squared. That looks a whole lot more. That looks a whole lot like another variance term, right? So that's kind of the way that we're going to be able to understand this term. It's like the variance in the learning procedure itself, right? Given a particular model and given a particular, you know, way of learning that model, you know, how different is the model that I learned to the average model that I would learn, and take the square difference of that. That's the variance, right? Plus f bar of x prime minus f of x prime squared. You'll notice that I didn't put an expectation around that thing. Why did I not put an expectation around it? It's because there are no random variables in there whatsoever, right? There's no d, there's no y prime. There's nothing random about this second expression, right? This second expression is basically asking, well, let's take out the randomness in the model learning. Let's just look at the average model that I would learn, okay? How does the average model that I would learn compare to, this model, this true function that I'm trying to approximate, right? That is, in some sense, it gives you an understanding of, is my model what we call well specified, right? Does it have enough capacity, enough power to represent the true function that I wanted to learn, irrespective of, the data that it's actually being trained on, right? Like, let's take that out of the equation and just try to learn on average, is my model good enough in order to learn the underlying function, okay? That's what the second term is, that's what the second term is trying to get at here. And then I have sigma squared. Yes. F bar, right, is essentially F bar is informally speaking, F bar is like the average model, right? But the way to sort of formally describe F bar is it's some function that when it's given an input x, we have to think about what prediction does it make on that x, right? The prediction that it makes on that x is if I averaged over all the models' predictions on that x, where all the models are trained on different data sets, right? So actually, maybe we can go back a couple slides and I can show you something like this, right? So when I'm looking at something like, F bar for like some new data point like over here, right? If I'm looking at F bar for a new data point over there, here I have, predictions that are like this, and that. Those are not all that different. If I average all of those together, there's like a pretty small spread, and I get an average that's like, pretty close to all of those predictions, right? Whereas if I look over here at that same, point, right? Sorry. Right. So that is what F bar is. And then what we can say, right, is like, well, how does that compare to like what the actual function value is at that particular point? That's going to tell me what my bias is, right? Like my bias is, even if I averaged over all the models that I could learn and then made a prediction, how wrong would I still be, right? Regardless of like the data that I actually used to train on, right? And so high bias essentially indicates that my model is underpowered, right? Because it can't make the right prediction regardless of whatever data we give it. Does that kind of make sense? And then the picture over here for overfitting is a little bit more complicated. I don't know if it would work pictorially because, these were kind of just drawn haphazardly. But we'll talk about that in a second. Yes? That's exactly right. So it's an average over, F bar is an average over like all the possible models that we can get, for different data sets. It's making the average prediction there. Okay. Here's that same equation again, typed out. I think I reordered the first and second terms, but it's the same equation, I promise. This first term that we have here, okay, this is the square of a quantity that we call bias. Okay, bias is actually a very, very general statistical term, right? That basically means if you're trying to estimate some quantity, how different is the estimate in expectation from the actual underlying quantity, right? So that's what bias means in statistics. Here, bias is being applied to understanding generalization error for regression models, right? This bias is basically trying to tell us exactly what statistical bias usually tells us, which is how wrong is my model on expectation, regardless of the data set that it's trained on, right? So here we've completely removed the expectation part because there are no random variables associated here whatsoever. There's no D, right, in particular. So it's not saying like what would we learn on a particular data set. It's what we learn on average, given all the different data sets. And then how wrong is that average F bar from the model that I'm really trying to learn. And here we can really start to associate this with the idea of underfitting, right? Because if I can't even learn anything good on average, that just means that my model's not specified well. That means that it's going to underfit the data, and it's just not going to do a particularly good job at predicting for new data points because it wasn't able to learn the underlying function to a sufficient degree of accuracy, right? Whereas the second term is a very classic example of, variance, right? We all know what the statistical definition of variance is, and this is just the variance in my learning procedure, right? The variance in estimating theta from a particular D, right? What's really interesting about this term over here, okay, and something that I actually neglected to mention until now, is that if you look at this term and you stare at it hard enough, you'll actually notice that there's no F, okay? There's an F bar and there's an FD, but there's no F, okay? That second term actually has nothing to do with the true function whatsoever, right? That second term is only a quantity that characterizes the learning procedure, right? It doesn't care what the true underlying function is. It's just asking for the learning procedure, for the model and algorithm that I specified, how different is that model going to turn out, every time I relearn it compared to the average, okay? So that's the variance in the learning procedure itself. So regardless of whatever the true function f is, how much does my model change based on the training data set? And we saw in like the previous slide, right, where we're learning all these crazy functions, right? That as my training data changed, my model that I learned also changed a lot, right? Because it was really overpowered, it was able to fit all that data, and that's why we related to the concept of overfitting, right? Because my model is really expressive, it's able to fit all my data really well, but it still might make errors, right, if I don't have enough data, and that's characterized by this variance, right, in what model comes out of the learning procedure. And then the last term that we have, sigma squared, is what we call irreducible error. Irreducible because we're assuming that it's just a part of the problem, right? The higher the irreducible error, the harder the learning problem is, but there's nothing that we can do about that, right? It's just a noise in the data process itself, and that also factors in a very important way into the errors that we might make, into the generalization error of my model. Yes? Interesting. Yeah, so when we do cross-validation, right, cross-validation is really trying to, cross-validation, just like validation, is really trying to prevent us from overfitting, right? That's the goal of cross-validation, is to sort of select hyperparameters that's going to make sure that my model is not too powerful, right? And it can't just fit the data in some really weird way, right? Cross-validation does reduce the variance in your estimate of true risk, because you're doing this training validation split multiple times rather than a fixed training validation split. That is true. I'm not exactly sure. I would have to think really hard about how that relates to this variance over here, which is the variance of your learning algorithm itself, which is there's multiple different sources of variance along the way. I think that these two are kind of separate. A useful thing to try to do on your own, think back to that picture from lecture 1 with the different bullseyes and try to understand why that is the intuitive picture behind these quantities, bias and variance, okay? So remember, the picture for bias was like all of your shots are like way far away from the bullseye, right? So that's kind of like a systematic, how wrong are you, even if you have like the data that you need, right? And then the picture that we drew for variance, right, was like the spread was really large, right, in terms of the shots, but maybe they were centered around the bullseye, maybe they were, right, but the spread was very large, and that's kind of like the variance of your learning algorithm. How differently does your model turn out depending on the data set, right? So it's good to try to understand these mathematically, but also connecting that back to the intuitive picture is is also important. So just as a quick final note about this part, traditional statistics, very much thinks of this decomposition, this bias variance decomposition, as a quote-unquote trade-off. Okay, what does it mean by trade-off? It means that very traditional thinking is that you increase variance, and if you decrease bias, the cost that you incur is that you'll increase variance. Okay, so if you decrease your chances of underfitting, right, by decreasing bias, making your model more powerful, you are necessarily increasing your chances of overfitting, of increasing your variance, because you might not have enough data and your model is going to overfit the data that you do have, right? This is a very typical way to think about generalization error, and then if it's really a trade-off, right, then what that would suggest is that there's some sort of sweet spot, right, in terms of how complicated your model is, what kind of featureization you use or something like that. There's a trade-off, which is kind of the sweet spot where you've minimized, the bias plus the variance, right? And this is, all of these different U-shaped curves that you might see in traditional statistics textbooks. That's kind of the trade-off that they're trying to illustrate, right? However, over the past few years, there's been, a lot of interest in trying to understand for deep learning, which is, kind of a topic that we'll talk about near the end of this course, why that doesn't really seem to be the case anymore. And it seems to be the case that we can sort of escape all of these issues that come with this trade-off and actually just keep cranking our models up more and more and more, making them really, really, really complex, way more than how much data would suggest, right? And then still getting a really, really good model despite that. So it seems like maybe this bias variance decomposition is not as much of a trade-off as we once thought it was, which is why I didn't call it that in the slides. It's best to understand it as a decomposition, and whether or not it's really a trade-off is the subject of much ongoing research. So we won't talk very much about that at the moment because not a lot of people really know. Okay, now we are ready to do a very shallow dive into decision theory, which is our other topic for today. Remember, it doesn't actually really have a whole lot to do with everything that we've done so far, but both of these topics are quite interesting, and we'll give a brief treatment to both of them. So let's switch gears and talk about classification models, okay, our favorite. In classification, just like in regression, right, we usually don't have the case where, things are deterministic, right? Like, it's not usually the case that our input X is going to uniquely specify Y. Instead, X specifies some distribution over Y, which is why we build probabilistic models, right? And then our predictions are guesses. They're educated guesses about what we think the most likely, label, the most likely class would be, but we're very rarely ever sure about what the class should be, right? And so we need to make these guesses, and so the question is, how do we make these guesses? Well, we've already talked about this concept of a classifier, right, as being a combination of a model, right, something that, takes in an input and then outputs some kind of maybe distribution or some scores or something like that. And then we combine that with an actual decision rule, right, which takes the output of the model and then turns that into, a discrete prediction, right? And the rule could be something as simple as predict whichever class has the highest predicted probability, right? It's, usually something as simple as that. But decision theory actually is a very rich field, which asks questions such as the following. What is the best decision rule? Actually, this one might seem pretty straightforward, at least, in a very simple case, and as it turns out, it is pretty straightforward. But when is it not the obvious one, right? So what's the obvious one? Probably the obvious one, at least in the context of probabilistic models that you can think of, is predict whatever class has the highest predicted probability, right? That's kind of the one that we always default to, that we always think about. When is that one not necessarily the best one to choose? Are there cases where it's not the best one to choose, right? And another question that we can ask from the perspective of decision theory is, are there some guesses which maybe we should not make? Okay, so is it ever the case that maybe we actually want to abstain from trying to make a prediction? And what types of situations are those? So without going into too much detail, because we only have 5 minutes left anyway, let's take a brief look at some of these questions. A lot of decision theory hinges on the idea of being Bayesian, okay? which is basically, doing things according to Bayes' rule, according to things like the Bayes optimal decision rule, and thinking about Bayes' risk and all of this other kind of stuff. Okay, but really, it's not all that complicated. Let's just draw a pretty simple, intuitive explanation of what might be going on here, right? So here, what I have is some toy one-dimensional problem, okay? So this is x, okay, my single feature that I have as an input. And then here, what I've actually denoted with these different bell curves, these are histograms of x. So think back to something like LDA, for example, right? Where we assume that each one of my class conditionals, right, x given the first class and x given the second class, they both come from Gaussians. So these are like histograms over the different distributions of my two classes, right? So I can specify that, like, here's my, class that I arbitrarily assign the label +1, and then here's the class that I arbitrarily assign the label -1. And then these are the different class conditional distributions, okay? So the Bayes risk, right, when I'm looking at it from this perspective, it basically just asks, what's the probability of being wrong, okay? So integrated over all my x, right, and then the prediction that I make for all x's, what's the probability of error on average that I might make, okay? And if I want to minimize the probability of being wrong, it turns out that, it's pretty simple to show that there's a very simple answer to minimizing the probability that I'm wrong, which is to pick the class that has the higher probability, at least in the two-class case, right? I just pick whatever class has the higher probability, and that decision boundary, the Bayes optimal decision boundary, lies right here, just like you would expect it to, okay? So what I'm going to do is I'm going to make predictions according to whichever class has the higher probability. If I'm on this side, I'm going to predict minus. If I'm on this side, I'm going to predict plus. But as you can see, right, if I have a certain amount of noise inherent to my process, which is the case with like these overlaps, right, then I'm not ever going to be perfect, right? Unless my classes were truly perfectly separated, right, I'm never going to be perfect, and there's always going to be some amount of error that I still incur. Oops. Yeah. Some amount of error that I still incur, which is represented essentially by like this area under the curve over here, right? This is the error that I still incur. This is the Bayes risk. I can never fully get rid of this amount of error that's just inherent to the process, right? But the Bayes optimal decision boundary kind of minimizes that risk, and we do so by essentially predicting whatever class has the higher probability. That minimizes the probability that I'm wrong, okay? But it's a very interesting question to ask, well, when might this decision rule not minimize my loss? Okay, so loss, oftentimes we have defined it so far as the probability of being wrong, okay? But loss does not necessarily have to be just, 1 if I'm wrong and then 0 if I'm right. Maybe there are actually different consequences to making my different decisions. That's kind of a big part of decision theory, right? So like, for example, if, plus is like, the prevalence of, the presence of some disease, and then 0 is like, or minus is like being healthy, you don't have that disease, right? Well, there are different consequences associated with predicting whether or not whether you have that disease or whether you don't, right? So if an individual is healthy and your machine learning model says you have this disease, that's pretty bad. It's not really maybe not the end of the world though. It's a false diagnosis, and then you have to go run some additional tests, something like that. There's a cost there, right? But if an individual has a disease and then you predict that they're healthy, that could be really bad, right? Because then they go home, they think that they're fine, and then you didn't catch this early on. Maybe that has really big ramifications in terms of, their future health, right? So if, for example, I have the case where my loss function L for, let's say that, the true label is minus, okay? And then my predicted label is plus. And like I said, maybe in this particular example, this is bad, but it's not the end of the world. If I have it such the case that this does not equal the loss of the true label being, yes, you have this disease, and then the predicted label being, no, you do not. Maybe this is like much higher or something like that, right? If that's the case, then you might not want to draw this decision boundary straight down the middle, right? Maybe you want to hedge your bets a little bit and be a little bit more likely to predict, yes, you have this disease, even if that's not the most likely class, right? So maybe you draw your decision boundary like somewhere out here or something like that to try to minimize this loss that's different from just the probability of being wrong. It actually assigns different weights to these different mistakes that you could make, okay? So that's one example. The last example, which I don't think I'll have a lot of time to talk about, is if you want to abstain entirely from making predictions, sometimes maybe that actually is possible,